We're going to look at linear differential equations, which is not actually a topic specifically included in the AP curriculum. However, they do like to throw this kind of differential equation on the test as an FRQ sometimes. And so I think it's worth looking at and kind of recognizing them. Notice the form of it. It's dy dx equals some constant times x plus some constant times y plus some constant. The fact that those are all just a constant times the variable to the first power, there's no other function types in there, that's what makes it a linear differential equation. That does not mean that the solution curves are all linear, right? There actually is one linear solution on every linear differential equation. And one of the things we're going to look at is how to find that. But as for the other solution curves, we're actually not going to find those because I don't know, what is this differential equation not? Like what, in terms of types of differential equations we've learned about and the types we've learned to solve, this one is not, it's not the kind we learned how to solve. What's the kind we learned how to solve? It's not separable, that's right. We know how to solve separable differential equations using separation of variables. You can't separate these variables. I mean, not in the way that separation of variables works, right? Here's why. If you tried to, move the dx over to the other side, you'd be looking at dy equals, you have the dx up here, and then you have all this junk in here. And with separation of variables, you have to be able to get all of the y stuff with the dy as a function that's multiplied by dy. You have to be able to do that. You have to get like g of y dy, right? Or let's say f of y, I guess, f of y dy. And then on the other side, you have to be able to get, g of x dx, right? You have to be able to get a function of y times dy, a function of x times dx. You can't get that from this. And I'm stressing this a lot because on the AP exam, when they ask this kind of problem, a lot of Calc students who, maybe didn't go that deep into these are going to think, oh, I'm going to solve that. I'm going to do separation of variables. Sometimes they'll even in the question, they'll talk about a particular solution. They won't say find it. They'll just kind of talk about one. And and so students will be like, oh, I got to find the particular solution. I know what that is. And they'll start doing separation of variables and they'll like subtract the by over here. It doesn't work. You'll do something that's just completely incorrect, do a lot of work for no reason, and you'll get no points, and may God have mercy on your soul, right? All right, so instead of that, you're not going to be asked to solve these for a general solution and then a particular solution other than the linear solution. Let's look at a specific example and see how to do that. So specific example, we'll say dy dx equals 2x plus 3y plus 6. This is the one we're going to look at. And very likely on this, if you get this kind of a problem as an FRQ, the first thing you'll probably be asked to do is make a slope field, with like 6 or 9 or 12 points on it or something. And then they might ask you to find the second derivative. We'll do that in a little bit. They might ask you to find the values of m and b such that y equals mx plus b is a solution. That's what I want to look at first. Find the values of m and b such that y equals mx plus b is a solution to this differential equation. They won't call it a linear differential equation because, once again, that specific type is not in the curriculum as a thing to be studied. So it's just a differential equation they're giving you. There's a way that they intend you to do this, and I'm going to show you that way first. But then later I'm going to show you a way that's actually simpler that I think you'll like better. So first of all, this way, actually maybe you guys can think of this. At the beginning of studying differential equations, one of the first things I asked you to do is I gave you a differential equation and I gave you a solution to a differential equation, and I asked you to verify that the solution was in fact a solution. And with some of those problems, we even had to find some constants in the solution to make it so. So this is that same idea. How do I do that? How do I verify that this is a solution, or find the values of those constants that make it a solution? Any thoughts? Yeah. Exactly. We're going to plug y, which is mx plus b, in for the y, and we're going to find y prime. What's y prime? True. But what is y prime for this solution? M. Yeah. You can do the derivative rules up there, or you can just think it's a line. The slope is m. Derivative gives you the slope, right? And we can take m, and we can plug that in for y prime. And that gives us an equation we can work with. So that's what we're going to do. We'll do that first. dy dx, I'm going to use m there. And then I have 2x plus 3y, which is 3 times mx plus b, right? And then plus 6. So I don't know, maybe this doesn't look like that helped much, because now we have one equation and it's confusing because it has 3 different letters in it, right? So you might be thinking, how do you solve for 3 variables in one equation? But these aren't all variables. M and B are constants that we just haven't found their values yet. X is the only variable here. And we're not actually solving for X. X is truly a variable here in that X can be anything, right? And that's the key to this. We need values of M and B that make this equation true for all values of X. Okay, it has to be true no matter what X is. So what I'm going to do is kind of rewrite this equation. We'll make this 3mx plus 3b, distribute there. And then what I'm going to do is kind of group things here. I'm going to put the 2x terms together and actually factor out the x. So I'll do 2 plus 3m times x. And then I'm going to group the constant terms together, 3b and 6, plus 3b plus 6, and I'll throw parentheses around them for good measure. On the other side of the equation, I just have m. Good? I could even throw the m over here if I wanted to and set it equal to 0. That would work as well. But this is fine. And you know what? I'm going to write one more thing on the left side, because here's the deal. On the right side, I have an x term. Let me make that line a little smoother. And I have a constant term. On the left side, though, I just have the constant term. I'm missing the x term. So I'll write an x term there. Since there isn't one, it's 0x, right? So there's my x term. And if I want this to be true, like I said a minute ago, for all x, this isn't one equation. It's actually 2 equations in there. The x gives me my 2 equations, right? If these are going to be true, if this is going to be true for all x, then the green parts have to be true by themselves, and the purple parts have to be true by themselves. If that doesn't totally make sense, let me just make this point a slightly different way. If I told you, much more simply, if I told you that mx plus b equals 3x plus 7, what values of m and b make that true for all x? You would all tell me that m has to be and b has to be 7. If it's going to be true for all x, these have to be the same line, right? They have to be the same. So the only way that's true for all x is if m equals 3 and b equals 7. Sure, there are other lines that will intersect this line, that it'll be true for one point. But if I want it to be true at all points, it has to be the same line. It has to be true for all x. So this is really the same idea here. If this is going to be true for all x, then the x coefficients have to be equal by themselves, and the constant coefficients also have to be equal by themselves. And so I get 2 equations from this. And I can leave the x off. I get 0, because 0x equals 2 plus 3m, because 0x has to equal 2 plus 3m times x. And then I also get m equals 3b plus 6. And so I can solve now for m and b. I start with the green one because it only has one constant in there to solve for. Subtract 2, divide by 3. And then over here, I can now plug that in for m. Do a little work here. Oh, I should have done that in purple. And what negative 2 was, that negative 18 thirds, so negative 20 over 3, and then divide by 3 again. So b equals negative 20 over 9. Look good? And that one's a little bit annoying, that number, but yeah, I mean, there it is. M equals negative 2/3, b equals negative 20/9. What that means is that the line y equals negative 2/3 x minus 20 over 9 is a solution. Whoops. Is a solution to this differential equation. And it's actually the only linear solution to that differential equation. Does that make sense? Cool. I'll show you another way to do that in a minute that's actually easier, I think, and ties into some other stuff we're going to have to do. But first, let's look at this on Desmos. So let me make sure I have the same equation first of all. 2x plus 3y plus 6 is dy dx. So I'm going to go to my slope field generator. 2x, oh, I have minus here. 2x plus 3y plus 6 is what we use. So let me backtrack there and make that plus. And here's my slope field for that differential equation over here on the right. And I don't know if you guys can kind of see the solution curves in there. Right now, if you look at that, that movable point, here, I'll move it over here a little. If I was trying to draw the solution curve through that point, as I go up to the right, it's aiming kind of really steeply up to the right. It's just going to kind of go up really steeply, right? But if I follow it kind of down this way, I would keep going. It's turning as I get closer here. It actually really turns quickly here. And if I keep following its path, it's going to end up having me go, sorry, it's kind of a tight needle to thread here, but it's going to really get me going almost in a line. It's actually approaching a slant asymptote there. Guess what that slant asymptote is? Yeah, exactly. It's that line we just found. It's the linear solution. So let me put it in there. I have a spot. Oh, hold on. I was messing with the window. You know what? Actually, I'll leave the window alone. So let me go back here. What was our coefficient for the slope? Was it negative 3/2? Oh, negative 2/3. Cool. Thank you. Negative 2/3 x, and then minus 20 over 9. Yeah. And if I turn that line on, there it is. Can you see how that line kind of fits the slope field? It's a little tough to see because it's turning so sharply near that line. So, but you can see all the slopes near that line are pretty close. If I zoomed in with the y values here, it would probably be a little more clear to see also. So like even though you have some of these that look like they're about to cross the line, as they get closer, it turns really close to that line, okay? So what's happening is on this kind of differential equations, there is one linear solution, and then every other solution curve out there has that line as a slant asymptote. So all of the curves above the line are concave up, which is something we'll talk about in a minute. And as you go up to the left, they approach that line asymptotically from above. All the curves below the line, all the solution curves down here, they also, off to the right, they go down very steeply, but as you go up to the left, they will approach that line asymptotically also. They're all concave down below the line, which brings me to another question that they like to ask on the AP exam with these questions. They might ask you to find the second derivative, and then they might ask you a question about where the solution curves are concave up or concave down. Sometimes they'll just say, describe the region in the XY plane where the solution curves are concave up, let's say. So if they ask us to do that, here, let me scroll down here. Describe the region in the XY plane where solution curves are concave up. Then again, first they might even prompt you to find that second derivative. If they don't, you're gonna find the second derivative. So we start with our first derivative, the differential equation, right? dy dx equals 2x plus 3y plus 6. Sorry, I had to check what that was again. And how do I find the second derivative then? Well, derivative of 2x is, oh, whoops, where's the, I wrote 2x plus 3x. It was 2x plus 3y, right? Okay. So what's the derivative of 2x? 2, yep. And what's the derivative of 3y? 3y prime, very good, which is, that's y prime, right? So that whole thing is going to get plugged in. And of course, the derivative of 6, 0. And so we get 2 plus, and then we're going to distribute 3 into y prime. So we're going to get 3 times 2x, which is 6x, 3 times 3y, which is 9y, and 3 times 6, which is 18. And then I'm going to simplify. It equals 6x plus 9y plus 20. And so that's the second derivative of y with respect to x, or y double prime. And if I want to know where the curves are concave up, what's like the natural thing to do with that? What would I do? Y double prime is greater than 0, right? Set it greater than 0. When the second derivative is positive, my curves are concave up. So what I'll do is I'll take this expression for y double prime and I'll set it greater than 0. 6x plus 9y plus 20 is greater than 0. And what I want to do is just solve that for y. Because if I'm going to describe the region, it's easier if you kind of have y isolated. You could say what kind of function it is and where we are. It's a linear inequality is what it's going to be. So if I isolate y, let's keep the inequality. Divide by 9. Hey, those numbers look familiar, right? That's that same line. We're getting y is greater than that because we were solving an inequality where y double prime is greater than 0. So what I would say in answer to this question, this is the way they would show it on a scoring rubric for the AP exam. They would show this work, and then you just want to say the solution curves are concave up above the line y equals negative 2/3 x minus 29ths, right? Like if you were back in Algebra 1, when you guys did linear inequalities, you'd graph the line as a dotted line because it's just greater than, and then you'd shade above it, right? So that's the region where this is true. Whoa, almost dropped my marker. That's the region where this is true, is above that line, and that's where this is true. That's where the second derivative is positive. That's where the curves are concave up. So that's my answer. Solution curves are concave up above the line. And since I'm saying above the line, now I'm going to give it as an equation. Y equals negative 2/3 x minus 20 over 9. As I pointed out, though, that is that same line that was the linear solution. So I want to talk about why that is, and that's pretty much the last point I want to make here. Does anybody have an insight into that? Why is that line that's like the dividing boundary for where y double prime is positive and y double prime is negative? Why is that line the linear solution? And this is something I really just realized like last year because I was looking at these linear differential equations and the types of questions they ask, and I was like, this is really the same question, right? You get the same answers. Here's the deal. We're looking for a linear solution up here, right? A linear solution to this differential equation, right? What's true about the second derivative of a linear solution? Yeah, people are saying 0. It's 0, right? Every line has a second derivative of 0, right? The first derivative is a constant. It's the slope. It's m. The second derivative then is the derivative of a constant. It's 0. Also, if you think about what a second derivative tells you, it tells you the concavity of a curve, right? It tells you like how it's curving. Lines don't curve, right? Their second derivative value is 0. So with that in mind, another way to attack this question, which is really asking what is the linear solution, is to just find that second derivative, which was pretty easy to do, right? Find that second derivative and set it equal to 0. And it's really the same work. Whoops, I'm like having trouble here. It's really the same work we just did, isn't it? We set it greater than 0, but setting it equal to 0 is like the same thing. We're just solving then for that. So if you take second derivative, y double prime equals 0, you get 6x plus 9y plus 20 equals 0, and that will yield this line. But as an equation, when we solve, we'll get y equals negative 2/3 x minus 20 over 9. And I think that's actually an easier way then to get m and b for the linear solution than what we did in here. Does that make sense? Either one's totally fine, but yeah, that's just, it connects. And if you're going to be asked to do other stuff, like say where the curves are concave up and concave down anyway, so you're going to have to find a second derivative anyway, you may as well get the linear equation that way too. Good? All right. That's all I wanted to show you with linear differential equations. So I have a problem up on the board here that you guys are going to try. If you're watching this video later, it's the 2015 AP Calc AB number